Bueno, muy buen día para todos. Esperamos que estén todos muy bien. Muchas gracias por unirse nuevamente a esta nueva edición de los Viernes Tecnológicos que hoy vamos a desarrollar con el acompañamiento de Coperion en una presentación que va a presentar avances e innovaciones en el eje de sistemas de mezclado y, por supuesto, en la variable de la precisión y la certeza que estos sistemas pueden proporcionar según la tecnología actual. Mi nombre es Matías Pulcinetti. Para que todos me conozcan, mi rol en FICEM es director del área de concreto y los voy a acompañar durante esta sesión como moderador de este espacio. Hoy tendremos a Steve Becker. Él es quien va a desarrollar la presentación de hoy y adelantándome un poco a lo que van a ver a continuación, va a ser una presentación en idioma inglés, pero que va a estar apoyada con un subtítulo en español, de manera que todos lo van a poder seguir, entendemos, sin ningún tipo de problema. Simplemente por esta cuestión del idioma es que ustedes van a ver inicialmente una reproducción en video que ya incorpora ese subtítulo y que lo hemos pensado de esa manera para que todos puedan seguir el tema con la mayor comodidad posible. Antes de presentarles esta intervención, quería compartir con ustedes un breve video sobre FICEM para que todos nos conozcan un poco más. Eventualmente, algunos de ustedes no conocen tanto a FICEM o no han tenido oportunidad de participar en otros webinars. Y un poco el objetivo de este video es que nos conozcan un poquito más. Así que así avanzamos si les parece.
Estamos presentes desde hace miles de años. Resolvimos las necesidades de la humanidad y cumplimos sus sueños. El cemento y el concreto son el cimiento que sustenta el progreso y permite construir nuestros anhelos. Soportan el paso del tiempo, resisten a condiciones climáticas adversas y nos brindan seguridad. Un material tan único como insustituible, tan disponible como asequible, tan responsable y promotor del desarrollo económico como social. Con cemento y concreto podemos construir viviendas dignas, pero, por sobre todo, hogares, puentes y carreteras, conexiones que verdaderamente importan. Centros de salud y educación, pero, antes que nada, calidad de vida. Nuevos horizontes y futuros prósperos, con equidad. Nada de esto sería posible si no contara con una industria visionaria, responsable y comprometida con la sostenibilidad, con la firme decisión de lograr la carbono neutralidad 2050. La industria del cemento y el concreto es sinónimo de innovación, progreso y tecnología, con una búsqueda permanente de la mejora continua de procesos y productos, enfocados en la circularidad, la descarbonización, la biodiversidad, el bienestar de los trabajadores y las comunidades y la satisfacción del cliente. Con estos objetivos y bajo el liderazgo de la Federación Interamericana de Cemento, FICEM, la industria en América Latina y el Caribe es consciente de su rumbo. Traducir con cada acción la agenda global de sostenibilidad en una estrategia regional y nacional propia y a la vez posicionar esa visión regional en el escenario mundial. Somos 26 países, 77 empresas productoras de cemento, 13 asociaciones, cámaras e institutos, más de 20 aliados y producimos anualmente 200 millones de toneladas de cemento en 270 plantas y moliendas. Por eso somos capaces de construir un futuro sostenible y resiliente para todos. FICEM, potenciando la fuerza de nuestros asociados y representando la industria a nivel global, fortaleciendo el relacionamiento de la industria y difundiendo sus logros. Somos la voz de un sector comprometido con la sostenibilidad. FICEM, la voz de la industria regional. FICEM, una sola voz. Todos somos FICEM.
Bueno, entonces, ahora sí, permítanme presentar a Steve. Steve Becker es director senior del eje, por decir una manera, de la unidad de negocio vinculada a Systems Sales Minerals. Él pertenece a la firma Coperion. Coperion es una compañía global con más de un siglo de trayectoria en ingeniería de procesos y manejo de materiales a granel, reconocida por sus soluciones de alta precisión para dosificación, transporte neumático, mezcla y sistemas completos de procesamiento. Con presencia internacional y una fuerte base tecnológica, la empresa atiende a industrias como el plástico, química, alimentos, minerales y materiales de construcción, ofreciendo equipos y sistemas diseñados para maximizar confiabilidad, eficiencia y control en operaciones críticas. La unidad Coperion Process Solutions trabaja de forma directa con los sectores de cemento, agregados y energía, aportando soluciones robustas y precisas para procesos de alimentación y blending. Steve es ingeniero profesional con más de 40 años de experiencia en el manejo de materiales a granel, habiendo trabajado en investigación y desarrollo, ingeniería, aplicaciones, ventas y gestión. Ha liderado iniciativas de sostenibilidad y reducción de carbono durante más de 2 décadas. Posee 2 patentes en equipos para manejo de materiales y ha publicado y presentado trabajos técnicos en conferencias internacionales. A lo largo de su carrera ha acompañado a cientos de plantas industriales en la optimización de sus procesos. Actualmente, les decía, es senior director de la unidad System Sales Minerals, donde aporta su profundo conocimiento técnico y su experiencia en soluciones para la industria del cemento y de los minerales en general. Así que, bueno, recién les mencionaba, esta presentación va a ser en idioma inglés, pero van a tener a disposición un subtítulo en idioma español. Y bueno, para facilitar ese mismo vehículo es que esta presentación ha sido pregrabada y es lo que vamos a mostrarles a continuación, como si fuera un seminario en vivo real. Así que los invito a escuchar esta presentación y luego, por supuesto, vamos al momento de preguntas.
Hello, everyone, and welcome to today's presentation on accurate cement blending. Thank you for joining us today. And I also want to thank FICEM for organizing this program and this event and giving us the opportunity to speak to you today. My name is Steve Becker. I am going to speak to you today about cement blending. I've gotten almost 40 years of experience in bulk material handling in various R&D, engineering, sales, and management roles, and have done a number of papers and presentations throughout the world on various topics. But probably the best part of my job is visiting plants and facilities around the world and helping to improve their processes and seeing the way people have their facilities operating. So just a few words about Coperion. So Coperion is the world leader in feeding, conveying, size reduction, filtration, and thermal processing. You may have known us previously as a Schenck Process FPM in North America. And Coperion now incorporates several brands, including Coperion rotary valves and pneumatic conveying equipment, Raymond Mills, which you might be familiar with, Bartlett Snow thermal processing equipment, stock equipment in the power industry, and of course, some of the former Schenck process equipment that you might be familiar with. Just taking a quick look at our global footprint, you can see we're located all over the globe with facilities to support your needs, both on the pre-sale side, during the sales process, and then after at commissioning and installation and support services as well. So let's talk about what we're here to do today, and that is accurate cement blending. So our goal today is to discuss the importance of accurate blending systems and how to drive efficiency, quality, and sustainability in cement manufacturing, aligning with the evolving industry standards. The backbone of the modern cement blending operation consists of advanced technologies like Coriolis-based measurement, which we'll go into quite a bit of detail, just-in-time blending, and precise feeding and metering. This allows for a very flexible manufacturing process to adjust to the ever-changing SCM availability and concrete blend requirements. This system works very well with all types of SCMs like fly ash, blast furnace slag, CKD, calcined clay, limestone, pozzolana, and many others. So on the picture here, you'll see a typical configuration of what we'll talk about here today, including the silos for the constituents at the top and then the loadout of the blended cement at the bottom. And as I mentioned, we're going to talk today about Coriolis-based flow meters and measurements, just-in-time blending and how we blend kind of on demand, and also the importance of precision feeding and metering, and then talk about some of the additional process equipment that's required to pull this whole system together. So as I mentioned before, you may know Coperion from some of the other products that we provide to the cement and lime industry. We've got here our alt fuel systems, which we can feed biomass and refuse to both the main burner and calciners. We have screw pump replacement valves that can replace screw pumps with a more energy efficient rotary valve. We've got the cascade blending systems, which is what we'll talk about here today, where we're going to blend different constituents into a blended cement. Also using the Coriolis technology as our solid fuel metering systems, which works well with petcoke and pulverized coal. And then also one of our many weighing and feeding pieces of equipment, including our weigh feeders, flow meters, and other feeders that we have to offer. So today we're going to talk about blended cement. And if you look at this process flow sheet of the cement process, you can see we're going to be talking about everything back here at the tail end of the process. So this is where the finished cement is blended with various SCMs right before it's sent to the customer, depending on the requirements of their local regulations, departments of transportation, or whatever the architect or contractor has requested. So before we get too far into that, I'd like to go through some definitions. So here, let's talk about feeder and meter. A lot of times those two terms are used interchangeably, but there are some differences that I'd like to talk about, and it's important to understand how the system operates to know this. So first, let's talk about a feeder. So a feeder is really any device, and that they typically could have a screw or a belt or even a vibratory tray that accepts a set point that you would provide as the plant operator for a specific feed rate. And then that device can control and maintain that feed rate by adjusting the speed of the internal feed mechanism based on feedback from the load cells that are also internal to the machine, and then change and measure that change in mass over time. So that includes equipment like belt feeders, loss and weight feeders, both fall in that category. And I've got a picture here on the side here showing a loss and weight feeder. This happens to be a screw feeder, so it's got an integral hopper where it maintains a level of material. We've got load cells on either side of here that measure that loss in weight of that hopper during the process. This happens to have a screw connected to a motor here in the back, and then that screw speeds up and slows down based on the signal that we're getting from the load cell as the material feeds out over time. So that's what a loss in weight feeder looks like. Now, in contrast to that, a meter is a device that only measures the material flow or the feed rate in the process. It doesn't control it necessarily, it just measures it. So whatever's going to pass through that flow meter, we're going to measure what that is. But we can take that flow meter and turn it into a feeder by controlling an upstream external feed device. That could be a screw or air slide or a belt, and we'll talk about those a little bit later. So there's several types of flow meters: impact flow meters, deflection flow meters, and Coriolis type, and they're all classified here. So I've got a picture of a representative Coriolis meter here. We've got an input and an output, so you can see whatever comes into the top here we're going to measure through this meter and then discharge it out the bottom. But we have no means to really control what's going in here until we add a separate device to this, an external device to this, and then our meter can control that external device, but it doesn't have the means to change the feed rate on its own. So in these blending systems that we'll talk about today, we use both feeders and meters. And the meters that we're going to use them as a feeder, controlling an upstream device to keep the recipe accurate. And the size and the type of the feeder or the meter is going to be determined by the material characteristics and the desired flow rates required. So this is a very key point that we've found in accurate blending is you have to have a very accurate dosing system to dose those constituents. So no amount of blending can make up for an inaccurate proportioned ingredients. If you were making a cake and let's say by mistake you added too much salt to that cake mix, it doesn't matter how much you stir it, how much you blend it, how much you mix it, you are not going to alleviate the problem of having a salty cake when you're done. So the importance of adding those components into the proper ratio initially is really the only way to get a good blended system. So we start designing our systems with very accurate metering and dosing equipment to ensure that we have the best short-term and long-term accuracies. So I've got some examples down here of a couple different flow meters designs. This is a lower rate size flow meter. This is a higher rate size flow meter. You can see the pre-feed device coming in here. And then we will also use some of these loss and weight feeders that we talked about earlier. And this picture here on the side illustrates how we kind of put those feeders, those meters together to create a blending system. And we'll go into that in a little more detail coming up. But first, I'd like to talk about what our options are and what are the choices we have available for feeders and meters. So for these low rate additives, so I'm going to say approximately 3 tons per hour or less, we can usually use either a loss and weight feeder or a small belt feeder. The advantages of this equipment is they can feed at very low rates. They have a very large turndown range over a significant, and have some significant configuration flexibility. So we can change out screw diameters, we can change out lengths, nozzle discharge configurations, hopper sizes, a wide variety of components. And then on the belts, we can also change out the depth of the material on the belt width, and the belt speed, and those all can manage at the feed rate range. So because we've got that large flexibility, they're very, very good for feeding low rate materials. We can also select one of the several model sizes that we have available. So they come in a couple of different sizes to maximize the min rate and the max rate to optimize the range that you're looking to feed. So the accuracies with these feeders are very, very good. As I had mentioned, usually we're at plus or minus 0.5% accuracy as long as they're properly configured. And some examples of these are the Mechatron or K-Tron single and twin screw loss and weight feeders, or small wave belts like we've shown here. Now, the options we have for high rates typically are much, much higher. And these are typically for the high rate additives and OPC, which we're blending together. We typically would use a flow meter configured with a pre-feed device to make these a feeder. So the advantages here is we've got high accuracy at rates over 2 tons an hour, and even up to volumes as high as 1,200 cubic meters per hour. So very, very high volumes here. Again, we have several models to pick from to maximize the accuracy and the desired range. So we've got a couple different variations, so you're not using the equipment on one end of the range or the other. When configured properly, we can minimize the wear from abrasive materials, which most of the materials we're dealing with are typically fairly abrasive. And we can adapt them to several pre-feed type devices, air slides, screws, or belt conveyors. We'll talk about those coming up in a later slide. And there's several technology options to balance that cost and accuracy. So to give you an example, we see accuracies typically plus or minus 0.5% up to 2%, which are achievable depending on the technology you select. So if you use a an example, a deflection chute flow meter like you'll see right here in this picture, we typically see a plus or minus 2% accuracy with that device. It is, of course, a lot simpler device and less expensive. But if you want a higher accuracy, say plus or minus 0.5% accuracy, then we tend to go to the Coriolis flow meter. And in most blending applications, accuracy, as we said, is very important. So we tend to gravitate to the Coriolis flow meter for most of the weighing in these blending type systems. So let's talk a little bit more about the Coriolis feeder. So as I mentioned, we typically will use them at least for the final weighing mechanism, if not for all the weighing mechanisms for the higher rate materials. And we measure the mass flow in the blended cement in real time. So we're measuring as it passes through. This flow meter is really unaffected by factors like the material velocity, density variations, wind. So you're not subjected to a lot of variations in weighing. So it's a very reliable piece of equipment. And this technology also enhances accuracy during blending, ensuring optimal proportions. So we make sure we maintain those optimal proportions and maintain good product quality with those good accuracies. What makes the Coriolis really fit this blending system well is the unique design of the measuring rotor. And it provides a very excellent means to blend the material as it passes through the flow meter. So we really get to do two things at once. We get to measure it very accurately, and then we blend it as it exits the flow meter. And we'll talk about how that Coriolis feeder works in the next slide, but just to kind of go through some of the pictures I've got here. So here you can see a kind of a cutaway version of the flow meter with the material coming in through the top of it. And then we've got this rotor here, which I'll explain a little bit later in the next slide. But you can see as the material passes through there, we get a very good blending situation happening there. This picture here in the middle shows an actual rotor. We take an access port off of one of the flow meters, and you can see the rotor itself inside the machine. And then this picture here on the far right shows you kind of a cascade system again, where we'll put these configurations together. This one uses a multi-core and a loss and weight feeder, and then another flow meter, Coriolis flow meter here at the bottom to do the final weighing and the blending of that system together. So let's look a little bit deeper into the Coriolis feeder details. As I mentioned, the unique design of this meter provides not only very accurate metering, which we'll talk about here a little bit, and then also the added benefit of the inline blending. So this technology of Coriolis flow meters has been around for quite a while. It was utilized for many, many years in the liquids measuring industry. And through the years, it's been adapted to be able to use in the bulk solid material industries as well. And this technology has been in use for bulk solid material handling for over 30 years now. So it's a very well-proven technology. So let's take a look first on the right here at this flow meter. This is kind of what I would call the anatomy of a Coriolis flow meter. The configuration may vary slightly from model to model, but in general, they have all very similar components. So let's start here at the very bottom where we have that rotor, the rotor we talked about before. Material comes in the top of that rotor. There's a small a deflection cone in the middle around that shaft. As that rotor is rotating at a fixed speed, the material hits that cone, works its way out across these rotor fins, and then works its way out to the outside and then discharges to the bottom of the feeder. So you can imagine if you've got any materials coming in here, separate streams of materials as you enter into the top of this rotor that's operating at a fairly high speed, you're going to see a very good blending and mixing as it runs through the rotor, and then as it's mixed back together inside of the housing of the multi-core as it exits. So that's where the magic happens with the Coriolis meter. Let's look further up here. So that rotor is attached to a shaft, which is attached to a motor, and that motor is driving this rotor at a continuous speed where we're sensing the speed using a speed sensor. And then we have a mechanism here that with a load cell that actually measures the torque, the reaction torque that that motor has to drive that rotor at a continuous speed. And in the next slide, I'll go through the math a little bit with you, but what I can tell you is that the rotor torque is directly proportional to the mass flow. So the more material that's flowing through this multi-core, the more torque this motor is going to require to maintain that rotor at a constant speed. And as the material load reduces or the feed rate reduces, you're going to see a less torque required from that motor to keep that rotor at the constant speed. So that's how we use the measurement device of the multi-core to measure that flow rate. So this picture here on the left kind of goes through what I already talked about. We've got a continuous fixed speed rotating measuring wheel in a dust-tight body. That's another important aspect of this is it's completely contained. Everything is enclosed and the material never exits the material flow. So everything is very dust contained and it's a very concise, maintenance-free housing. And then when we get that torque measurement and that motor speed, that data is communicated to a control module in our disaccount control system. And then we use that information to then control the rest of the system, pre-feed devices, other feeders, things like that. So here's another example. You'll see the material coming in the top. It feeds down through this diverter chute into the rotor. And you can see as the rotor is rotating, this material's coming out of that rotor in a very consistent, well-blended condition. And this kind of shows you a little free body diagram of what's happening on the rotor. But let's take a look at the next slide where we'll go into the math. I won't go in there too deep, understanding this is a lot to go through, but I'll just give you a quick review of the math that's involved here so you know that I'm not just lying to you. So as you know, force equals mass times acceleration. Our force here is the Coriolis force that we're measuring on the rotor as the material passes through it. M is the material mass, so that's the mass of material that's feeding through here. And the acceleration is the Coriolis acceleration. That's the Coriolis force that we're imparting on that particle as it's moving across that rotor. So if you do a bunch of other math and a lot of solving there, you can solve for mass flow, which is the mass coming out of the bottom here is equal to the motor torque divided by the rotational velocity times the radius squared. So this denominator here, we can keep constant because we have a speed sensor on the rotor that we're going to maintain a constant speed. So omega here is going to be constant. And the radius of the rotor doesn't change. It's going to be the same all the time because we're not going to change the rotor. It's passing through the same path. So R is the same. So what we end up with was we have motor torque divided by a constant, which says that then the mass flow is directly proportional to the motor torque. And that's why these are so accurate machines, is there's no other variables in here that can affect that. And when we measure that motor torque, we can measure it very, very accurately based on the configuration of the system that we have. So moving on to taking that Coriolis flow meter, now that we understand how that works, we're going to turn it into a feeder. So how do we do that? As we mentioned before, we're going to add some type of a pre-feed device. And the way that control loop works is we've got a flow measurement, so materials coming down through our flow meter. If you look here on this picture, we've got the Coriolis flow meter sitting here on the floor. We've got a short little air slide coming out of a bin with a control valve right here. So our Coriolis meter is running. We see material flowing through here. We send the signal of what we're measuring to our control. Our control compares that to the set point that we have given it to say, I want to feed it X tons per hour. It will then adjust our pre-feed device, in this case here, a valve on an air slide. It will adjust that pre-feed device, open that valve or close that valve, depending on what we need to make that adjustment. The material flows out from that control device across the air slide down to the flow meter. And then we measure that again, and we continue this loop over and over and over again until we can maintain a very accurate feed rate accuracy. Now, in the time that I just explained that, the control in the system probably would have done it 100 times or 150 times or a lot of times. So this is continually running, and it's a very fast control loop so that we can make very fast adjustments and keep the accuracy very high. Now, looking at what some of the flow meter pre-feed devices we would typically use, let me start with an air slide. This is probably our preferred device for a number of reasons. They're very common in cement plants and lime plants already. They're used for various reasons because of their minimal wear that they can produce, because the material is so fluidizable. It's a very easy way to move the material, and very, very accurate flow control adjustments. So what we've got here is a cutaway showing the actual representation of what that control valve looks like. There are various designs and notches and things. We don't make air slides, we use air slides, but the air slide manufacturers can really help you dial in on the best control valve design for the material and the situation that you have. And then here you can see another example. We've got the bin here. We've got some manual valves to do some maintenance on the control valves. And the air slide, here's our control valve in this situation, and our air slide going down, feeding our flow meter. So this is an arrangement, as I said, we prefer. There is, for a number of reasons, minimal wear is obviously one. It is limited to free-flowing materials. Most of the materials that we're talking about, most of the SEMs and the OPC we deal with are free-flowing, so that's usually not too much of an issue. But they must run downhill. They rely on gravity to get the material to move. So if you've got a fairly long run from the bin or hopper to where the flow meter is located, it could be a little problematic because you do need some height to make that adjustment. And sometimes we just don't have the height to allow that material to flow downhill. Some of the other pre-feed devices which we will use include screw feeders. So screw feeders are another very good way to accurately control as long as they're properly sized. And one of the big advantages with the screw feeder is you can actually elevate materials. So whereas with the air slide, we have to make sure that we're downhill from where the material enters the air slide. With a screw conveyor, we can configure it to actually raise material up. And you'll see in this picture over here on the right, we're doing that. We've got the flow meter here sitting through the floor. We had some process piece over here, which we had to get the material over to the flow meter. So we've put in this feed screw that brings the material up and gets it to the flow meter. Now there is some requirements for screw feeders that we do want to maintain. There's a minimum RPM that works best because we don't want pulsations going to the flow meter, because that control loop's going to see material and then no material and material and no material, makes it hard for it to control. So by increasing the speed of this screw, we can make sure that we don't have those pulsations and the accuracy is maintained. And then one of the other devices that we will use is a rotary valve. So this is, you're probably very familiar with rotary valves as well. A very good device we use in line with the flow meter. Has excellent pressure and temperature isolation. So if you've got a high pressure or high temperature situation above the flow meter, we would definitely want to isolate the flow meter from that. So rotary valves are very good. But much like a screw conveyor, we can have abrasion and wear situations because a lot of the materials we have are very abrasive. So we can have wear on rotors, bearings, seals, all the things like that. So, so those are the three that we tend to typically use. They do have their own advantages and disadvantages. And as we work through the process of identifying a system, we typically will try to select the best one based on the application and the different materials we have available. So now we're kind of ready to put all these together and take a look at how do we configure all these pieces of equipment to give us a blending system. So let me start by going through that. We've got very accurate feeders now. We've got flow meters with pre-feed devices. We've got a very fast-acting control loop, but we somehow need to get blended cement out of this. So here's how we configure it to do that. So let's start up here with this picture with these two bins or silos. We'll call it material A and material B. And we'll work our way through this process and this configuration. So material A, we're going to extract out of this bin. Through here, we show an air slide and a control valve. We're going to extract that down out of that bin. It's going to go run downhill, and we're going to feed this flow meter here. We'll call that material A's flow meter. So materials A's flow meter is going to get a set point from the recipe that we have established. And we're going to control this control valve to hit that set point. So we're running that control valve or that control loop all right here in this situation, maintaining a very accurate set point feed rate that we have run to this device here. Typically, we'll do this for the largest recipe of whatever that recipe calls for, the largest constituent. So typically that'll be the OPC that we're going to blend the other additives to. So once we have that material A running through its flow meter and we're feeding at the proper rate, it's going to flow down and flow into this second flow meter, which we're going to call the final flow meter. So that final Coriolis flow meter is measuring not only the material that's coming down that we're measuring from material A, but we're also going to extract material out of this bin over here, bin B, through another air slide and control valve, and that's going to drop directly right into this flow meter. So no other flow meter or weighing device on this leg. We're just going to drop it down directly into that final flow meter. So since we know the total that we're producing here, and we know how much of material A we're putting into the final flow meter, we can calculate that the total minus A gives us how much material B is. And the control will actually look at that ratio to make sure that we are having the correct amount of material B in this total blend. And if we don't have that correct ratio, this control loop on this flow meter will start adjusting this control valve here, and we will increase or decrease the amount of material B flowing into this arrangement so that we get the correct ratio of material A to material B as it comes out here. Now, again, it took me a long time to explain that. This happens in a few seconds as the material runs down through those meters, through those air slides, and that control loop is operating, firing through in milliseconds. So in the time it took me to explain that, we probably would have already passed enough material through here to load a truck or a rail car. Looking at adding additional material, so this one we just have two materials. If perhaps you've got a third material that you want to add into this blend, we can just add another leg into this inlet chute coming in, add another weighing device, and then that weighing device would control that material C coming in. And again, we would do the same math. The total is A minus C, and then we would adjust B to come up with the proper ratio, and on and on and on. So you can see we can add almost an infinite number of additives as we go through here. And then let's say, for example, we're not always going to feed material B. Sometimes we'll do material B, and then sometimes we'll do a material C. We can add another leg from another silo into this chute work, and then we can either run material B for one recipe. Next recipe, we can switch to material C, feed it through this leg, and get the blended ratio for the blend containing material C. So as you can see, very flexible design. We just need to add and subtract components to get what we need. But the end result is you've got a very well blended cement, because as all these come down through this final flow meter, we're going through that rotor, which is spinning with those vanes, and then hitting the sidewalls of this meter and coming back together, ending up with a very, very well blended inline cement material. So we talked about some of the benefits of inline blending. Let's talk about them here on this list. So obviously we can save some storage silo capacity because we can blend on demand. So you won't have to run a 15% fly ash material. You don't have to run, say you won't have to run like 500 tons and put it into a silo. You can just run that as needed and run it right into a truck or a rail car as you need it. And then as the next truck or rail car comes in, we can switch that to a 10% fly ash blend almost immediately. Some plants will blend the cement in the mill, so they'll run that back through the finish mill and add the SCM into the finish mill and run that through. That does work, and that's a good way to do it. However, you do take up some mill capacity by doing that. So if your finish mill is already running near capacity, you don't want to lose that capacity. And so by putting this blending system downstream of the mill, you can run your mill at capacity and not have to worry about changing the grinding or the classifier or any of the equipment in the mill circuit as the fly ash goes in, or limestone or whatever. You can optimize that mill for grinding clinker, since it will only grind clinker. We also eliminate the need for a secondary mixer, blender, or a pug mill. This reduces a considerable amount of space, might even reduce an entire floor in a blending tower. And it reduces the capital and operating costs. A lot of times these mixers and pug mills have very large electrical motors that have a very large electrical draw, and by eliminating that piece of equipment, you've eliminated that electrical requirement and save some operating costs as well. We're accurately proportioning those additives in there, as we talked about, and as I mentioned, we have an almost unlimited number of ratios we can use, and blends and recipes we can use. The control is very adaptable to take a number of different recipes and hold them in and accurately measure and meter to those recipes when called for. And as I mentioned previously, the entire system is completely dust contained. Sometimes these pug mills and blenders, you need to access them, and so they don't always seal the best. But with this system, everything is sealed up tightly. We do have some flex connectors you see in this picture here, but those are very robust and don't typically see a lot of wear, so they last a very long time before you need to replace them. So let's look at some of the other equipment that we would typically use in a blending system. Let's talk first a little bit about pneumatic conveying, or I would say how you connect the dots. We've got these process pieces now, but we need to connect them up between different process steps. So one of those is pneumatic conveying. We would use this a lot when you're looking at unloading a truck or a rail car with the SCMs. If the truck or rail car comes into the plant carrying your fly ash or ground blast furnace slag, you somehow need to unload that and get it up into the silo, and that silo typically can be very high. So we typically use pneumatic conveying to do that, particularly if the truck comes in as a bulk truck. So we can do both lean or dense phase conveying. I won't go into the details of that in this lecture, but that just has to do with material to air ratios, and both of those have their own place depending on the material characteristics, the convey distances, what the transport rates your desired are, and then what's the most economical capital and operating costs. This picture here you'll see as a dense phase pump. So this is very common for large feed rates of a very abrasive material. They run at very low velocities, so the wear on the pipe and the components is relatively low. This picture here shows a diverter valve, and you see kind of a close-up of that diverter valve here. So if you do have a truck unload or a train unload station, we can have one single connection to that truck, and then you can have diverter valves along the pipeline to dump it into various silos. So if the truck you have now is fly ash and the next truck that's coming is blast furnace slag, you can divert that next truck into a different silo using pneumatic conveying diverter valves. This is we call this a sphere type valve, or this is a valve that's used for very abrasive materials, typically on the top and bottom of these pressure pots as well. So we have various uses for those. And this last picture here just shows you kind of a long run from a process point out into a load out facility with a silo. So very flexible, very adaptable, and as I said, connects those process points. Next one I'd like to talk about is filtration. So environmental regulations and employee health and safety are very, very important in the plants today. And air filtration really helps with both of those and is an important part of any process that we put into a plant. So air filtration is very common in silo venting, transport air venting, air slide venting, transfer points, process filters, and all these need to be designed to specific requirements and make sure that they meet your local regulations and also your plant permits. They should be selected with the correct media for the application, material, and airflows. And we have several technologies available, from traditional pulse jets, as well as very energy efficient medium pressure units, which use their own internal blower and not compressed air. So again, some opportunities for energy savings there. And I would recommend that you look at suppliers who have years of SCM filtering experience, because they are pretty difficult to handle and filter at times. And you want to make sure you get the correct sizing and filter media selected the first time, rather than having to go back and resize things later. So next, we've got this blending system concept that we just went through using the Coriolis flow meters. Still might be a little difficult to grasp, because there is a lot going on. There's a lot of parts that are moving around. There's a lot of configurations that we have together. So I'd like to offer this animation that demonstrates how the equipment's used and some of the technology that we discussed today. And so let me play that now, and it'll kind of give you, kind of tie together all of what we talked about here today. This video is on YouTube, so all you have to do is look up Coperion cement blending, and it's available right on YouTube if you want to take a look at it later. So I will be quiet, and let's watch the video. All right. Well, I hope that kind of tied everything together. Again, I would encourage you to download that video from YouTube, or take a look at it from YouTube and run through it a couple more times if you've got any questions on that. But I think it does a really good job in kind of pulling everything together and explaining visually what the process is that we're doing there. So next what I'd like to talk about, since we've got all these formulas we explained, we've got all these pictures and animations are really cool, right? But does this really work? That's the real question. So what I've got here to offer for you is a real life example that we can discuss. So this particular application is at Argos Rio Claro in Colombia. They are blending a calcined clay with OPC. This blending plant has been in operation since 2018, and it mixes a multiple number of ratios of clay up to about 30%, so some pretty high ratios. They have reported that they're consistently achieving coefficient of variations of less than 10. So if you don't know what coefficient of variation is, that is a statistical measurement of distribution in a population. So it'll tell you how much variation you've got from, say, sample to sample in a population. Now, the blending and mixing people will tell you that any coefficient of variation less than 10 is typically a homogeneous situation. So the results that Argos has been getting has been very, very good, very consistent, and very homogeneous in their operation thus far. It is the world's largest calcined clay operation, and that system includes 2 multi-cores Coriolis feeders, as you see here, one cascading into the other. They are fed from the feed silos by these air slides with control valves, so we've talked about that. And then here's a picture of those silos above the Coriolis flow meters in this blending tower. So here's some of the pictures. But again, I think what I'd like to offer to you next is a kind of a case study that we did with the people at Argos, which we appreciate their help here. And let me play that next.
I believe that blended cements are going to be the future of cements. This is a 1,500 ton per day kiln. It's the biggest and newest calcined clay kiln in the world. We want to produce every type of cement that we produce, not just have a very specific type 1 or type 2. We're going with whatever cement the market is requiring. That also required for the system to be adaptable. Each and every cubic inch of that material needs to be the same in order to be usable by the end user when they're building something. The team from Coperion, we sat down, we discussed the possibilities, we discussed the operation of the system themselves, and figured out whether or not, with a good degree of certainty, that would actually mix and there would be an homogeneous material at the end. Having the team from Coperion, led by Ernesto, developing with us, conversing every day from a technical point, that allowed us to get to a solution that, as you can see right now in operation, actually works. It was I was very proud to be in that team.
All right, so thanks to Argos for that review. And let me move on to our summary then. We're running out of time. So the key takeaways from this is any good blending system requires accurate feeding and metering. So these are essential to good blend ratios prior to the blending, and needs to be flexible to change with the different recipes and ratios as needed. The Coriolis flow meter we talked about in depth combines both metering and inline blending at extremely high throughputs and extremely high accuracies. And we get the addition of the blending mechanism of the weighing device as the material exits the flow meter. And then by putting all these things together in an inline blending system, we can optimize the processes for maximum flexibility, allow you to give whatever the cement market requires, you can make, decrease capital and operating costs while still providing excellent blending results and reliability. So I thank you for your attention today. And again, my name is Steve Becker. I'm the Senior Director of System Sales for Minerals at Coperion. My contact information is below. And should you want to contact me with any questions, I would be more than happy to field those. I thank you for your time today and look forward to your questions.
Bueno, perfecto. Hasta aquí la presentación de Steve. Vamos entonces a mostrarles ahora en pantalla un código QR para que puedan registrar las preguntas que tengan. Voy a dejarlo unos instantes, así pueden tomarlo con su teléfono o dispositivo móvil y allí tienen un formulario. Les pedimos que indiquen su nombre completo, la dirección de correo y la pregunta que tengan sobre este tema. Permítanme comentarles antes de hacer un cierre sobre esta sesión. Un evento muy importante que vamos a tener dentro de pocos días en Chile es la quinta edición del Congreso Cemento y Concreto Verde de FICEM. Este congreso, como saben, tiene un abordaje especialmente dedicado a todos los temas de descarbonización, agenda ambiental y muy conectado con todos los temas que tienen que ver con tecnología e innovaciones en el sector. Es un congreso que va a llegar por primera vez a Chile. Bueno, habitualmente en otras latitudes, en este año un poco más hacia el sur de nuestra región y esperamos que todos nos puedan acompañar. Así que naturalmente quienes tengan interés pueden ingresar a la dirección web que ven al pie de la pantalla, www.congresocedosverde.ficem.org. Allí van a encontrar la información completa, incluyendo la última versión del programa que tenemos y bueno, todo lo que necesitan para poder registrarse al evento. Por supuesto que si tienen alguna duda, nos escriben por la misma información que allí verán o cualquiera de los medios habituales de FICEM. Sepan también que esta edición del Congreso es algo particular en el sentido de que también no solo tiene el apoyo habitual de la Global Cement and Concrete Association, sino también de la ONUDI, la Organización de las Naciones Unidas para el Desarrollo Industrial, a través de un diálogo público-privado que vamos a tener embebido dentro del mismo Congreso, donde no solo vamos a poder discutir temas de tecnología, de procesos y todo lo que nos interesa como sector, sino también todo aquello que de alguna forma nos influye desde el punto de vista de la política y la regulación. Así que están todos más que bienvenidos y ojalá puedan acompañarnos. Tendremos varias visitas técnicas también, así que con seguridad van a poder tener un muy buen espacio y retroalimentación para sus funciones. Aquí les muestro un poco más de detalles sobre estas visitas. Va a haber visitas al inicio de la agenda. Esto es el lunes 11 de mayo. Y también tenemos una agenda dedicada al cierre de la semana para quienes están más interesados en temas de compensaciones basadas en el uso de soluciones basadas en naturaleza. Permítame mostrarles nuevamente el código QR. El día de hoy vamos a tomar estas preguntas y les vamos a enviar una respuesta por correo electrónico, un poco en función a la limitación del tiempo que nos ha quedado por la extensión de la presentación y también para acercarles más fácilmente una respuesta en español. Así que permítanos hacerlo de esta manera en esta ocasión y con seguridad van a contar con la respuesta que tengan a su pregunta. Antes del cierre, también compartirles un código adicional. Este código es un código de encuesta. Les pedimos si pueden allí dejar sus respuestas. Así, bueno, naturalmente también conocemos cómo mejorar esta serie de webinars de Viernes Tecnológicos al servicio de todos ustedes. Así que nomás por mi parte, nuevamente muchas gracias por haberse unido a esta sesión. Dentro de 2 semanas tendremos una nueva edición de estos webinars. Van a recibir dentro de muy pocos días la información y esperamos que nos puedan acompañar. Si quieren revivir este webinar, acuérdense que dentro de la sección de la Academia FICEM tienen a disposición todos estos webinars de manera que puedan revivirlos cuando gusten. Bueno, muchas gracias nuevamente. Buen día para todos y que tengan un buen resto de jornada. Adiós.